Welcome, everyone, to our presentation on the system design of WingSpan. We will delve into the key aspects of how WingSpan is designed to meet our objectives. Starting off with the architecture overview, let's dive into the Android application and web interface of WingSpan. Our Android app employs WebView to embed web content, ensuring a consistent experience across platforms. It seamlessly handles file uploads, crucial for image-based bird identification, with support integrated using Android's Web Chrome client. Our web interface utilizes AJAX integration for enhanced user experience, enabling asynchronous requests to the server. With Bootstrap 5, we ensure accessibility and visual appeal across devices and screen sizes. Transitioning to the backend server of our application, it's a Django app hosted on Heroku, with data stored in a SQLite database. The WingSpan app source code is managed with Git on GitHub. Our Django app is hosted on Heroku, which integrates with GitHub for a CI/CD pipeline, ensuring seamless deployment and keeping our app up to date for users. Our WingSpan app uses an SQLite database to store conversation history within HTTP sessions, enabling the application to maintain context during interaction. In WingSpan, intent detection is crucial for effective user query responses. User queries trigger an AJAX call to our backend API endpoint, handler request. The chatbot analyzes conversation history and the current message using a language understanding model, LLM, to determine the user's intention, ensuring accurate understanding and real-time response. Next, we'll delve into the machine learning models used in our application, as well as the integration of the LLM models in our application features. Starting with bird informational queries, our chatbot provides accurate bird information tailored to users' queries. We collected data on 415 common birds in Singapore using Python and Selenium from the Singapore Birds Project website. It's stored for easy retrieval, serving as an offline resource for our chatbot. We used the GPT-4 Turbo model to build our bird information system. Fine-tuning it with collected bird data, we made it searchable in OpenAI's Assistant API. Custom prompts allow semantic searches, effectively pulling relevant information based on user queries. To evaluate our model, we used Python test scripts to submit bird-related queries to the model via an API call. With a remarkable 95% accuracy rate, the model provides precise and contextually relevant responses. Our next feature, text-based bird identification, enables users to identify birds by entering textual descriptions or specific queries. We are making use of the same data used for bird informational queries explained earlier. The text-based bird identification model, using OpenAI's GPT-4 Turbo, handles inquiries about bird species. If the initial query doesn't yield a definitive answer, the system engages the user further by asking more detailed questions to refine the identification process. The model analyzes the user's query in real time, offering accurate bird identification with tailored responses, while gracefully managing any processing errors to ensure a smooth user experience. To evaluate our model, we use Python test scripts to submit various bird-related queries, each with pre-prepared correct answers. Our model achieves an overall accuracy rate of about 80%, demonstrating its reliability. The image-based bird identification feature enhances our application by enabling users to identify birds simply by uploading photos. We've compiled a comprehensive list of common bird names from the Singapore Birds Project, crucial for our model to correlate user-submitted images and ensure correct identification. When a user submits an image, it's resized, converted to JPEG, and encoded in base64. A detailed prompt combines the user's text query, the bird image, and a predefined list of bird names. The AI then analyzes both to identify the bird or suggest matches. Our model's performance is evaluated through Python test scripts that simulate real-world usage by submitting various bird images. Tests compare the model's identifications against a verified list of correct answers, achieving an 82% accuracy rate, showcasing its efficiency and reliability. Next is the bird sighting prediction feature. Data from the Singapore Bird Database is pre-processed for model training, involving multiple stages of transformation, cleaning, and feature engineering. Additional features from Singapore weather databases are also incorporated. We chose the random forest classifier model for bird sighting prediction due to its robustness with complex data and overfitting. We further tuned the model through hyperparameter tuning, selecting the best parameters via grid search and cross-validation. The classifier's evaluation, including precision, recall, F1 score, and support, varies across different bird species. Despite this variability, the overall accuracy achieved suggests the model's effectiveness in predicting bird species. The park recommendation system enhances birdwatching by suggesting parks where specific birds have been observed or are likely to be seen. It employs user-based collaborative filtering, adapting traditional recommendation algorithms for birdwatching. We collected historical bird sighting data from the Singapore Bird Database, including species, dates, and park locations, and normalized it using min-max scaler from Sklern for fairness in recommendations. We developed a user-based collaborative filtering algorithm with bird species as users and parks as items to predict bird sightings. Using the KNN basic algorithm from the surprise library, we identified parks with similar bird sighting patterns. We evaluated our model using five-fold cross-validation, focusing on RMSE and MAE. With mean RMSE of 1.1409 and mean MAE of 0.6776, our model shows high precision in predictions, reflecting a robust statistical analysis and practical understanding of birdwatching dynamics. Let's explore our heat map feature, visualizing predicted bird species counts in Singapore for the current week. We forecast bird abundance, providing real-time insights for birdwatchers and conservationists. We summarized unique bird species count data using pandas, calculating totals for each week and region. Longitude and latitude were used to visualize species distribution on the heat map. We calculated Euclidean distances between latitude and longitude data points to aid in feature engineering. Our model predicts weekly bird species counts using features like latitude, longitude, and the current week displayed on an interactive Plotly heat map. It offers insights into bird life trends by location and time, delivered as an HTML file for exploration. For our evaluation, MSE measures prediction error, while R-squared indicates model fit. Gradient boosting is chosen for heat map generation due to its higher R-squared and lower MSE. Thank you for your time today in listening to the system design of WingSpan. If you have any questions, please feel free to reach out to us.